Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Hello Urvija, hello Dayanand, hi Vila, hello the brainy bunch, hello Fahim, hi Anish, hi Ashwarya, hi Afshan, Mayank, Yuvraj, Varshini, Muntazir, Urvija. Welcome everyone, welcome back to NEET Elite. Just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys. Yes? Give me some green signal from the chat box, guys. Yes? Perfect. Good evening everyone, good evening. Welcome back to NEET Elite. Welcome back. Perfect guys. So as you all must be knowing, tonight it's going to be our 7th lecture from the chapter Atomic Structure. Okay, and in the tonight's session what we are going to do is we are going to discuss something really important, something very important I must say. That's what we call as hydrogen spectrum. Okay, I'm sure you guys are ready with your pen and paper, and whatever I'll be mentioning on the screen, I'll want you guys to take a note of every single thing which I'll be writing on the screen over here. Okay, so people, before starting the session, the ones who are new to the channel, let me introduce myself. My name is Wasim Bhatt and I'm your chemistry master teacher writer on this NEET Elite channel. Yeah, the ones who have not liked the video yet, please do like the video, share the video with your friends so that they get benefited out of these sessions too, and at the same time do not forget to subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which will be taking live on this NEET Elite channel, right? Okay, perfect. So do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. Yes, absolutely, your NCERT fingertips is good for chemistry NEET, absolutely, yes. Hello Fazan, how are you? Perfect guys. Perfect. So what all things we are going to do in the tonight's session? We'll be doing something called as hydrogen spectrum, right? Apart from hydrogen spectrum, we'll see something called as Rydberg's formula, and we'll try to solve some good questions based on this hydrogen spectrum and Rydberg's formula. Okay, perfect. Right. So people, you can let me know in the chat box, as I always say, if you guys are super duper excited about this session, right? Let me know in the chat box if you guys are super duper excited about it, right? Let me know in the chat box. Let me know in the chat box. Place it if you have not watched the earlier sessions of the atomic structure, then it will be difficult for you to understand it, okay? So let me know fast in the chat box if you guys are super duper excited about this session, right? Yes, absolutely, Harshita, you can watch it. If you are JEE Sprint, you can watch it too, no issues at all. Yeah. Perfect, guys, perfect. Thank you, Priyam, thank you. So people, this session, I'm going to start with few questions. And after doing those questions, we'll be coming to the hydrogen spectrum, yeah? Well, the first question with which we'll be starting the session is on your screen. Yes. Have a look on the question. See how this question is to be solved. Understand every single bit over here. Yeah? See guys, as per the question is concerned, radiation, just a second, yeah. Radiation corresponding to the transition n is equal to 4 to n is equal to 2 in the hydrogen falls on a metal of work function 2.5 electron volts. The maximum kinetic energy of the photoelectron emitted in joules will be. Understand this question and see how these sort of questions are to be approached. Understand properly, okay? See guys, first thing, I'm talking about something called as hydrogen atom, right? This is, for example, n is equal to 1 of hydrogen, right? This is, for example, n is equal to 2 of hydrogen, correct? This is, for example, n is equal to 3 of hydrogen, right? And this is, for example, n is equal to 4 of hydrogen, right? And over here somewhere you have got n is equal to infinity, right? Right now I'm talking about something called as hydrogen atom, okay? And for the hydrogen atom, we know the value of atomic number Z is 1. We know it, correct? First thing, in the hydrogen atom, the electron is making a transition from n is equal to 4 to n is equal to 2. So basically, the electron is present in n is equal to 4, and it is making a transition from n is equal to 4 to n is equal to 2, right here, okay? And we know, when the electron makes a transition from higher energy state to lower energy state, it emits energy, it emits radiations, okay? We know it. Now first thing which you all must be knowing, which we have discussed in the last session, see guys, energy of the electron in the second shell, which I'm representing by E2, is equal to minus 3.4 electron volts. I hope you remember this. And the energy of electron in the hydrogen atom when it is in shell number 4, its energy, which I'm representing by E4, it is going to be minus 0.85 electron volts. I hope you remember these values. If you do not remember, you can use the formula directly. And how do we calculate the energy of electron in a particular shell? Okay, the formula is En is equal to minus 13.6 Z square divided by N square electron volts, correct? Z value for hydrogen is 1, right? If you want to calculate the energy of electron in shell number 2, put the value of N as 2, right? You get the value as minus 3.4. Similarly, put the value of N as 4 in this equation, you get the value as minus 0.85 electron volts, correct? Right? Now people understand properly. We know, we have discussed, when the electron makes a transition from higher energy state to lower energy state, it emits energy, right? So how much energy this electron will be emitting when it will be making a transition from 4 to 2? Whatever will be the energy gap between these two particular shells, same amount of energy will be emitted by the electron. So first thing which I'll be doing right here, I'll be calculating the energy gap between these two shells, right? I'll be calculating the energy gap, which I'm representing by delta E, between these two shells. So what is the energy gap? See guys, 3.45 minus 0.85, correct? Sorry, 3.40 minus 0.85. So 10 minus 5 is 5, 13 minus 8 is 5, correct? Right? And it's going to be 2. So the energy gap between these two shells over here, it's going to be 2.55 electron volts. So basically, when the electron will be making a transition from 4 to 2, this much amount of energy the electron will be emitting. This much amount of energy the electron will be emitting, which is 2.55 electron volts, right? And when the electron is making a transition from 4 to 2, this much amount of energy electron is emitting, right? And this energy emitted by the electron, it is incident on what? It is incident on a metal which has got the work function of 2.5 electron volts, right? So basically, this is the metal surface over here. Let me represent it right here, okay? So this is the metal surface. How much energy is incident on it? 2.55 electron volts energy is incident on it, right? What is the work function phi of this metal surface? It's given to me as per the question. It's 2.5 electron volts, right? I need to calculate the kinetic energy. I need to calculate the maximum kinetic energy of the emitted electron, right? I need to calculate the maximum kinetic energy of the emitted electron, right? Okay. Yes. Very simple. Now people understand. Already I had given you one equation. If you remember, in the photoelectric effect, I had given you one equation. What was that? Incident energy is always equal to phi plus kinetic energy maximum. I hope you remember this. What do I need to calculate? I need to calculate the maximum kinetic energy with which the electron will move after the emission from the metal surface, right? Okay, understand. How much energy is incident on this metal surface? 2.55 electron volts. 2.55 electron volts, correct, is equal. What is the work function of the metal? It is 2.5 electron volts plus kinetic energy maximum, right? So by solving this equation, can I get kinetic energy, the maximum kinetic energy of the electron? Absolutely, I'm going to get it. It's going to be simply 2.55 minus 2.5. The value will come out to be 0.05. So this much energy, this much will be the maximum kinetic energy possessed by the electron when after the emission from here, right? Okay, I'm sure it's clear to everyone. But people, as per the question, are we supposed to calculate the maximum kinetic energy in joules or electron volts? We are supposed to calculate the maximum kinetic energy of this photoelectron in joules. And already I had given you one thing. 1 electron volt is equal to 1.6 into 10 raised to the power minus 19 joules. So simply, you are going to multiply this 0.05 with 1.6 into 10 raised to the power minus 19. You'll be getting the answer in joules. So basically, this much is going to be the maximum kinetic energy of the electron, right? Yes? You can let me know in the chat box if everything is clear till here. Let me know fast with some thumbs ups fast. No. This chapter is still going to take 4 more sessions. Guys, it's a huge chapter. It's a big chapter. It's not that small chocolate chapter, okay? Let me know fast if it is clear to everyone so that I can move on to the next one, right? Yes, Akif, these lectures are enough, yeah? Perfect, guys, perfect. Let's move on directly to one more question, which is again on your screen. Can you give it a try? This is the question which I gave as the homework in the last session as well, right? Okay. See guys, a very simple question, provided you know the relation to calculate the potential energy, right? Yes. See guys, the potential energy of the electron present in the ground state of Be tripositive ion. Okay, so basically I'm given something as Be tripositive ion, correct? If I ask you what is the atomic number of beryllium, you will simply say 4. This is the atomic number, right? The potential energy of the electron present in the ground state of Be tripositive ion will be. People, I hope you remember the formula to calculate potential energy. It is equal to, if you remember, it's equal to minus K ZE square divided by R. I hope you remember this formula. This is something which I had given you in the last session. Okay? Right? Now people understand. What is the value of Z? First of all, before putting the value of Z, what is K over here? K is basically equal to 1 divided by 4 pi epsilon naught. K is always equal to 1 divided by 4 pi epsilon naught. This is something which you will study in your class 12 physics as well in Coulomb's law, right? As per your Coulomb's law, F is equal to K Q1 Q2 divided by R square, right? Where K is something which we call as, K, where the value of K is 1 divided by 4 pi epsilon naught, right? Okay, just put the value of K over here. It's minus 1 divided by 4 pi epsilon naught. Okay, what is the value of Z? The value of Z is 4, so I'm writing 4 over here, right? It's going to be E square, and in the denominator you have got R. Can I see this 4 got cancelled? You got the value simply as minus E square divided by pi epsilon naught R. This is the potential energy. This is the potential energy of the electron present in the ground state of Be tripositive ion. You can let me know in the chat box if this question is again clear to you so that I can move on to something called as hydrogen spectrum. Yes? Right? Let me know fast. Absolutely, Kirti, you can watch it. Let me know fast if it is clear to everyone. Yes? Perfect, guys. Wonderful. Wonderful. Okay, so let's move on to something called as spectrum. Right? Let's move on to something called as spectrum. Hanirut, tomorrow we'll be having mock test for JEE 2020, for NEET 2021. Yeah? Okay. Now let's move on to something called as spectrum. How do we define the spectrum? What it is all about? It's a very simple concept, guys. Understand? See, as per its definition, spectrum, it is a collection of radiations of different wavelengths on a photographic plate. The collection of radiation of different wavelengths on a photographic plate is something which I call as spectrum. What it means exactly? See guys, all of you must have seen something called as prism. Okay, this is a prism, correct? Now, for example, this is the white light which is incident on this prism. This is a white light which is incident on this prism. Okay? Now, what is going to happen? What does this prism do? Can I say splitting of this light will occur, right? This white light will be getting splitted, right? Okay, this white light is going to get splitted like this. This is, for example, V, this is I, this is B, this is G, this is Y, this is O, and over here there is R, correct? The white light got splitted into 7 different colors. Violet, indigo, blue, green, yellow, orange, red. Every color over here corresponds to a particular wavelength. Or you can remember it like this, every color has got a particular wavelength right here. Okay, violet has got some wavelength, indigo color, it has got some wavelength. Similarly, blue, green, they have got different wavelengths, right? So basically, I got some 7 different colors like this. Okay, if I'll keep a photographic plate over here, this is a photographic plate. On this photographic plate, what is going to happen? First of all, this photographic plate, it is dark in color, right? You would have seen a photographic plate, it's completely dark in color, yes? Okay, right? Now people see, now people understand. Can I say on this photographic plate, I'll get some 7 different colors over here? Yes. And on this photographic plate, can I say I'll be getting 7 different colors, right? Every color corresponds to what? Every color corresponds to a particular wavelength. So basically on this photographic plate, I got what? I got a collection of radiations of different wavelengths. And this collection of radiations of different wavelengths on a photographic plate is something which I call a spectrum. Or you can simply say it is the image. The image formed on this photographic plate is something which I'll be calling a spectrum in simpler words. Yes? Okay? Right? I'm sure it's clear to everyone, right? So what is the spectrum? Spectrum is the collection of radiations on the photographic plate. Yes? Clear to everyone? Can you let me know fast if it is clear? Fast? Can you let me know fast if it is clear? Yeah? Right? Right. Perfect, guys. Perfect. Now people understand. This spectrum, which is basically the collection of radiations of different wavelengths on a photographic plate, it is actually of 2 types. The spectrum is of 2 types. One is called as absorption spectrum and one more is called as emission spectrum. Now what is absorption spectrum all about? What is emission spectrum all about? Understand properly. Someone is saying, sir, you wrote the VIB-GYOR in the reverse order. Did I write the VIB-GYOR in reverse order? So that's something which you can change on your own, right? Yeah? I hope you know that. Correct? Okay, let's move on then. Something called as absorption spectrum. Absorption spectrum, okay, what it's all about? It corresponds to absorption of light. What does that mean? You'll get the idea in some time. It corresponds to absorption of light, I'll say. Okay, what is emission spectrum all about? It corresponds to emission of light. Okay, what it means now? Have a look. Let's talk about the absorption spectrum first. Okay, first of all, I'm taking a container over here, and in this container I have kept a particular solution of some substance. I have kept a solution of some particular substance over here, right? I have kept a solution in this container. Now what is going to happen? Understand. First thing, let's assume a white light is incident on the solution. White light passes through this solution, for example. White light passes through the solution. Now white light, it consists of how many wavelengths? It consists of 7 different colors, right? Violet, indigo, blue, green, right? It consists of different radiations which have got different wavelengths, okay? Let's assume this solution, out of those wavelengths, out of those colors, let's assume this solution is absorbing, for example, 2 of the colors. Let's assume this solution is absorbing, for example, 2 of the colors, right? For example, it is absorbing blue and it's absorbing green. When the white light is passed through this solution, what this solution is doing, for example, I'm assuming this solution is absorbing, let's say, blue light and green light, okay? Right? So people, when this white light passes from this solution, I'm going to make it to fall on the prism, okay? What is going to happen? Again, splitting of light will happen. Right? But this light, which has come out of the solution, is it going to contain blue and green radiation? This light which has come out of the solution, it's not going to contain blue and green radiation. That means when the splitting of light will happen, the image which will be formed on this photographic plate, will the image contain blue and green color? The image is not going to contain blue and green color, right? Okay. So basically, this is, for example, your violet, this is indigo, right? Blue was supposed to be here. Blue was supposed to be here, but it won't be here, right? Why? Because blue light has absorbed. It has been absorbed, right? V, this is, just a second, this is V, this is I, this is B, this is G, right? G is also absorbed, right? So over here, there won't be any sort of spot on the photographic plate, right? V, I, B, G, Y, O, R, correct? So people, on this screen, what you will see exactly? You will see a violet color, you will see indigo, you will see, this was blue, this was green, right? V, I, B, G, Y, sorry, V, I, B, G, this is yellow, this is orange, this is red, okay? So on this screen, you will see violet, indigo, blue you are not going to see, green you are not going to see, orange you are going to see, red you are going to see, and so on, okay? So basically, over here at these two positions, you were supposed to have blue and green color. You were supposed to have blue radiation and green radiation. You were supposed to have blue wavelength and green wavelength right here, okay? But blue and green will be absent on the photographic plate. Why? Because blue and green has already been absorbed by the solution, right? So instead of this blue and green, you'll see some dark spots, right? There'll be as such dark spots on the screen, right? So basically, what you'll feel exactly, you will see on this photographic plate, you have got some dark spots on a colored background. You'll see some dark spots on the colored background, right? Okay, so whenever we talk about the absorption spectrum, what do we see exactly on the photographic plate? We see dark spots on the colored background, right? On the colored background. Why the spots? Why there are some spots blank as such? Why there are some dark spots? Why is that? Because those spots which corresponds to certain wavelengths which has been absorbed by this particular solution over here, right? Okay, what happened exactly? What happened exactly? Why the colors are missing? Why the colors are missing? See, this was a white light. This was a white light which was about to pass through this solution, right? This white light contained violet, indigo, blue, green, yellow, orange, right? And red at the same time, okay? Now people, in this solution, there will be some millions of atoms. I mean, there will be atoms in this solution, absolutely. Atoms have got electrons, right? I'll say some of the radiations, some of the wavelengths which corresponds to blue color and green color, for example, okay, they are being absorbed, right? Okay. When the atom is absorbing these radiations, I'll say atom is absorbing energy, right? So what would have happened? I'll say electrons would have got excited, right? Electrons would have got excited. So the light which is coming out of the solution, it will be containing all the wavelengths except your blue and green, right? So at the end on the photographic plate, you will see all the wavelengths except your blue and green, right? Okay, so what you're seeing, in place of blue and green, there will be dark spots. So you are seeing exactly dark spots on the colored background. This is something which I call as absorption spectrum. Can you let me know in the chat box if it's clear to you? Fast. Can you let me know fast in the chat box if it's clear to you? Can you let me know fast? Perfect. Now people, there is something called as emission spectrum. What is emission spectrum all about? Well people, in case of emission spectrum, what happens? The light from the source, is incident, it's incident on the prism, right? And different wavelengths are obtained, which corresponds to what? Which corresponds to emission spectrum. What it means exactly? First of all, the light which is coming from the source. Your source can be anything. Your source can be, for example, bulb, right? Your source can be sun. Your source can be excited atom, right? Your source can be excited atom. Okay, so basically guys, how you can understand, how you can visualize this, understand. Over here atoms have basically absorbed blue wavelength and green wavelength, right? Atoms have absorbed basically blue light and green light, okay? Now, when the atoms would have absorbed this blue and green, the electron in the atom, it would have got to the excited state, okay? remember, electron in higher energy states, electron in the excited state, it's very, very unstable there. Electron in the excited states, it resides there only for 10 raised power minus 8 seconds. The electron in excited state, okay, it just resides there for 10 raised power minus 8 seconds, then it jumps back to its original position. Right? And when the electron will jump back from higher energy state to lower energy state, it will emit radiation. And now the electron, which was excited by absorbing these two radiations, right, went to the higher energy state, but there it's unstable. Now the electron is going to jump back. When the electron jumps back, it is going to emit the same radiations which it absorbed. So on the photographic plate now, what do we see? We'll see only two colors. Those colors which it earlier absorbed, right? So on this photographic plate, you'll only see blue and green color, right? Okay. So people, can I say in this emission spectrum, when the electron is coming from higher energy state to lower energy state and it is emitting radiation, it is emitting the same radiation which it absorbed in the beginning, right? Okay. Yes. So people, on this photographic plate, you will see only those radiations. Which the electron absorbed in the beginning, right? So what do I see on this photographic plate now? Do I see dark spots on colored background? No, right? I see colored lines on the dark background. Let me write it. In the emission spectrum, you see colored lines on the dark background. Right? Okay, so over here you saw dark spots on the colored background. Now over here you are seeing the colored lines on the dark background, right? Okay, so people, remember this emission and absorption spectrum, we call this as photonegative of each other. We call these two as photonegative of each other. We call these two absorption and emission spectrum as photonegative of each other. Right? Can you let me know if it is clear to everyone what this absorption and emission spectrum is all about? Can you let me know with some thumbs ups fast? Yes? Let me know fast. So basically, when white light passed through this solution, okay, electrons got excited because this solution, it absorbed certain wavelengths, and the wavelengths which this solution absorbed, after that, it emitted the same wavelengths, right? Okay, and those emitted wavelengths, they formed the emission spectrum. Okay, and this is something over here which we got as absorption spectrum. I'm sure it's clear to everyone, right? Yes? Perfect. Anirudh, bro, I'm taking 3 channels, right? So I have to schedule everything for 3 channels. If it was only 1 channel, NEET Elite, which I would have been handling, for example, then I would have finished your course long back for the NEET 2021. But I'm currently on 3 channels. JEE channel, this NEET channel, and 1 more catalysis channel, okay? So I have to plan all the 3 exactly, right? So that's why sometimes my sessions get cancelled in this channel or in JEE channel or in catalysis channel, right? Okay, it keeps on happening. And moreover, apart from the YouTube sessions, I have the long-term sessions as well, okay? And apart from the long-term sessions, I sometimes take micro courses as well, right? Okay? Perfect, let's move on. So people, let me tell you, these were 2 spectrums. One is absorption spectrum and one is emission spectrum. Further, this emission spectrum, it's classified into 2 types. One is called as continuous spectrum, one is called as discontinuous spectrum, right? Okay, so this is something which I told you, dark lines on the colored background, colored lines on the dark background. Now let me tell you, this emission spectrum, it's of 2 types. One is continuous spectra, one more is discontinuous spectra, right? What is continuous spectra? In this continuous spectra, you won't be able to distinguish different colors. Like your rainbow. In your rainbow, you cannot distinguish all the 7 colors, right? Okay. So basically, in your continuous spectra, you cannot distinguish the different colors on the photography plate. But in discontinuous spectra, you can distinguish 2 colors on the photography plate. Yes? This discontinuous spectra, it's further of 2 types. One is called as band spectra. one is called as line spectra. What is this band spectra? Band spectra, it consists of discrete bands of different colors. So what you get on the photographic plate in band spectra, see, this is for example the photographic plate, so you get bands of colors. This is for example a red color, right? Okay. You get, for example, one more band of, for example, blue color, right? Okay, so this is something which I call as band spectra. You get a band of color. You get a band of color right here. But in case of line spectra, what do I get? See, if this is a photographic plate, I get some colored lines like this. Okay, I do not get band. I do not get band of colors. I get line. I get lines which corresponds to different colors or different wavelengths, right? Okay, so remember in short, your spectra, it is a collection of radiations of different wavelengths on the photographic plate. It's of two types, absorption, emission, right? In absorption spectrum, what happens? We get dark lines on the colored background. In emission spectrum, we get colored lines on the dark background. Emission spectrum is further of two types, continuous, discontinuous. In continuous, you won't be able to distinguish the colors on the photographic plate. In discontinuous, you will be able to distinguish the different colors on the photographic plate. This discontinuous, it is of two types. One is called as band spectrum, one is called as line spectrum. In band spectrum, you get a band of color, but in line spectrum, you get different lines of different colors. That means having different wavelengths. Yes? Let me know in the chat box if it is clear till here, so that I can move on to the actual topic which we have to discuss basically in the tonight's session. Yes? Let me know fast in the chat box. No, Irfan, it's not announced yet. Okay, these are all the rumors. Perfect. Perfect, guys. Now let's move on. Let me tell you two important points. Remember, band spectrum, it's formed by molecules, and line spectrum, it's formed by atoms. Remember this? Okay, this is something which you need to remember. Band spectrum, it's formed by the molecules, whereas your line spectrum, it's formed by the atoms. And if I talk about hydrogen atom in particular, what kind of spectrum hydrogen atom shows? Hydrogen atom shows emission, discontinuous, and line spectrum. Hydrogen atom, it shows, hydrogen is first of all atom. If it is atom, then definitely it's going to show line spectrum, right? Because line spectrum is observed by the atoms, right? It's formed by the atoms, correct? Your hydrogen in particular, it shows emission, discontinuous, and line spectrum. This is again one more thing which I want all of you to take a note of, correct? Now we are going to move to the actual stuff. We are going to talk about the actual stuff. Now we are going to discuss about the hydrogen spectrum actually, okay? Which is very, very important. You would have seen in your textbook some Lyman series, Balmer series, everything is written. So we are going to talk about that now, okay? See guys, understand now what I'm going to do. It's very, very important. So now I'm going to talk in particular about the hydrogen atom, right? Let's assume this is N is equal to 1 for hydrogen, right? Let's assume this is N is equal to 2 for hydrogen. Let's assume this is N is equal to 3 for hydrogen, correct? Let's assume this is N is equal to 4 for hydrogen. Let's assume this is N is equal to 5 for hydrogen. And let's assume this is N is equal to 6 for hydrogen. Correct? And let's assume this is N is equal to infinity. N is equal to infinity, right? Which atom I'm talking about right here? I'm talking about the hydrogen atom, right? First of all, if I'll be having hydrogen atom with me, if I'll supply some energy to this hydrogen atom, what is going to happen? The electron, which is already in the ground state, it will excite to the higher energy states. It will excite to the higher energy states, right? Okay, if I supply some energy to the hydrogen atom, the electron in the hydrogen atom is going to absorb that energy, and the electron will make a transition from lower energy state to higher energy state. But the electron in the excited state is highly, highly unstable. It just resides there for 10 raised to the power minus 8 seconds. If the electron in higher energy states, if the electron in excited state is unstable, that means the electron will try to jump back to its original position. And when the electron jumps back from higher energy state to lower energy state, it emits radiations. It emits radiations, right? Okay? Yes? Now people understand. For example, I had the hydrogen atom with me. I gave some energy to this hydrogen atom. Electron in it, it got excited, right? Now the electron is somewhere in the excited state. It can be 2, 3, 4, 5, infinity, whatever. Now in the higher energy states, electron is not stable, not that much stable. It just resides there for 10 raised to the power minus 8 seconds. It jumps back. So remember, when the electron makes a transition from higher energy states to shell number 1, when the electron makes a transition from higher energy states to shell number 1, like this. Higher energy state can be anything, right? When the electron makes a transition from higher energy state to shell number 1, right? We get a series of lines called as Lyman series. Lyman series, right? Basically, when the electron makes a transition from higher energy states to shell number 1, right? We get a series of radiations on the photographic plate, which have got different wavelengths, right? And that spectrum which we get on the photographic plate of different wavelengths, right? That's something which I call as Lyman series. That's something which I call as Lyman series. So in your Lyman series, remember the lower energy state, which I'm representing by N1, that is 1, and your higher energy state, N2, it can be 2, it can be 3, it can be 4, till infinity, right? One thing, okay? Now the second thing, when the electron makes a transition from higher energy state to shell number 2, again I get a series of lines, again I get a series of radiations which have got different wavelengths on the photographic plate, right? So those series of lines is something which I call as Balmer series. This is something which I call as Balmer series. And in case of your Balmer series, your energy state, your lower energy state N1 is shell number 2, and higher energy state N2 can be 3, it can be 4, it can be 5, till infinity, right? This is the Balmer series, when the electron makes a transition from higher energy state to shell number 2. And similarly, when the electron makes a transition from higher energy states to shell number 3, what do I get? I get a series of lines called as Lyman-Balmer. This is Paschen. And in case of Paschen series, your lower energy state N1, which I'm representing by N1, that's 3, and higher energy state N2 is going to be 4, it can be 5, it can be anything, right? Similarly, when the electron makes a transition from higher energy state to shell number 4, we get a series of lines called as, this is Lyman-Balmer Paschen, this is called as bracket series. This is called as bracket series, in which the lower energy state N1 is shell number 4, right? And N2 can be anything. It can be 5, it can be 6, it can be 7, dash, 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 right? Similarly, when the electron makes a transition from higher energy state to shell number 5, the series of lines which we get over here, that's what we call as, this was Lyman, Balmer, Paschen, bracket, and now it's going to be Pfund series, PFUND. In Pfund series, lower energy state N1 is 5, the higher energy state N2 can be 6, it can be 7, and so on, right? And when the electron makes a transition from higher energy state to shell number 6, the series of lines which we get, that's something which we call as Humphrey series. That's something which I call as Humphrey series. And in case of Humphrey series, your lower energy state N1 is 6, and higher energy state can be anything, 7, 8, dash, 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 till infinity, right? Okay, I'm sure it's clear to everyone, right? Okay, now people, there are few important terminologies which you must know before doing the questions. What are those important terminologies? Understand. See, if I talk about Lyman series in particular, remember, in case of Lyman series, the lower energy state is the first shell of hydrogen, right? Higher energy state can be 2, 3, 4, 5, and so on, correct? And let me tell you, in case of Lyman series, this transition of electron from 2 to 1, this is what I call as first line of Lyman series. This, from 2 to 1. This is something which I call as first line of Lyman series, or I represent it by H alpha. This is something which I call as H alpha line of Lyman series. Similarly, this is something called as H beta line of Lyman series, H beta. Similarly, this is something called as the third one. This is something which I call as H gamma line, H gamma. Similarly, this is called as H delta, and so on. Similarly, if I talk about the first line of Balmer series, the first line of Balmer series means the electron is making a transition from 3 to 2. This is the first line of Balmer series, which I call as H alpha line of Balmer series. This is the second line of Balmer series, right? From 4 to 2, which I call as H beta line, H gamma line, and so on. Similarly, this is the first line of Paschen series. This is the second line. That means H alpha, H beta, H gamma, and so on, right? Okay. So from here, people, I want all of you to remember what is H alpha line, what is H beta. You need to be careful with these terminologies because these terminologies are frequently asked, right? Okay. Now one more thing. Understand. For example, if I take any of the line among the all, for example, I'm talking about H alpha line. If I'm talking about H alpha line of Lyman series, that means we are talking about the first line of Lyman series. And in the Lyman series, the lower energy state is 1. So the first line of Lyman series means the electron is making a transition from 2 to 1, right? And when the electron makes a transition from 2 to 1, it's going to emit energy. If I need to check the wavelength of the radiation emitted when the electron makes a transition from 2 to 1, या 3 to 1, या 4 to 1, or 5 to 1, or infinity to 1. How do I do that? That I do by a simple formula that's called as Rydberg's formula. So basically, Rydberg's formula is one formula by means of which you can clearly get the wavelength of the radiation emitted when the electron makes a transition from higher energy state to lower energy state. I'm sure you would have taken a note of all this, right? I'm sure you would have taken the note of all this. Okay, I'm marking a statement over here. Right? First thing, there is a formula called as Rydberg's formula, right? As I told you, Rydberg's formula, it is used to calculate the wavelength. It is used to calculate the wavelength of the radiation emitted. Wavelength of the radiation emitted when the electron makes a transition. When the electron makes a transition from higher energy states to lower energy states. Higher energy states to lower energy state. Okay. Right? Yes. And people at the same time, what is this Rydberg's formula all about? See, how do we write the Rydberg's formula? I'm writing something like this. There's something which we call as wave number, if you remember. There's something which I call as wave number, which is basically equal to 1 divided by lambda. Wave number is always equal to 1 divided by lambda. It's equal to r z square multiplied by 1 upon n1 square minus 1 upon n2 square. Right? This is something which I call as Rydberg's formula. But people, in this formula, while using this formula, you need to be careful with certain things. This N1 is the lower energy state. N1 always is the lower energy state in which the electron is. N2 is the higher energy state in which the electron will be. Right? This R is something which I call as Rydberg's formula. Sorry, Rydberg's constant. This Z is the atomic number of the atom. Right? Lambda is the wavelength which is emitted when the electron is making a transition from higher energy state to lower energy state. Right? Okay? Now people understand. This is something which I call as Rydberg's formula. Just a second. This is my Rydberg's formula, right? What is the value of this R? What is the value of Rydberg's constant? It is 109677 centimeter inverse, right? But in the problems, I won't be taking this value of R. In the problems, I won't be taking the value of R as this 1096 something. In order to reduce the calculation, I'll be taking 1 by R value as 911.5 angstroms. In order to reduce the calculations, I'll be taking 1 divided by R value as 911.5 angstroms. As simple as that, okay? Remember this as well, correct? In order to reduce the calculation, I'll be taking as 1 by R as 911.5 angstroms. Now, we are going to talk about this hydrogen spectrum a bit in detail. This was the basics of hydrogen spectrum, right? Now, let's move on and let's see basic things, different things in case of hydrogen spectrum. Okay, first thing, that's called as, let's try to analyze Lyman series. And in the Lyman series, I'm analyzing first line of Lyman series. First line of Lyman series, right? Okay, first line of Lyman series. We call it as H alpha line, right? We call it as H alpha line of Lyman series. First of all, in the Lyman series, the lower energy state, which I represent by N1, that's 1, right? Since it's the first line of Lyman series, so the higher energy state is 2. Basically, the electron is making a transition from 2 to 1, right? So when the electron will be making a transition from 2 to 1, energy will be emitted, right? Radiation will be emitted. That will have some wavelength, right? How to calculate that wavelength? I'll be simply using the Rydberg's formula. 1 divided by lambda alpha, right, is equal to R, Z is 1 for hydrogen, 1 divided by N1 square minus 1 divided by N2 square, right? Okay, so from here, you can calculate 1 divided by lambda alpha, right, is equal to R, it's going to be 4 minus 1, 3 divided by 4, right? Or you can say simply H alpha, right, sorry, not H alpha, lambda, when the electron makes a transition from 2 to 1, is going to be 4 divided by 3 multiplied by 1 by R, and 1 by R value already I have told you that is 911.5, and the answer is going to be in angstroms. So this is basically the wavelength emitted when the electron makes a transition from 2 to 1. This is the wavelength emitted in case of H alpha line of Lyman series, right? Okay, this is the wavelength emitted in case of H alpha line of Lyman series, correct? This was point number 1. This is how we use the Rydberg's formula and calculate the wavelength of the radiation emitted when the electron gets de-excited. Yeah? Okay. Now people, this was point number 1. Point number 2. If I talk about the second line of Lyman series, which I call as H beta line, right? Second line of Lyman series. Understand. First of all, in case of Lyman series, lower energy state is 1. Now I'm talking about second line. That means electron in higher energy state is in 3, right? That means the electron is making a transition from 3 to 1. And if the electron is making a transition from 3 to 1, it will be emitting a radiation which will have some wavelength, right? How do I calculate that wavelength? Same, I'll be using the Rydberg's formula. 1 divided by lambda is equal to R. Z square is 1 divided by N1 square minus 1 divided by N2 square, right? So it's going to be 1 divided by lambda is equal to R. It's going to be 9 minus 1, 8, 8 divided by 9. Or you can write lambda is equal to, just take the reciprocal, lambda is equal to 9 divided by 8 multiplied by 1 by R. And already we know 1 by R value is simply 911.5 angstroms. So you get the lambda over here as 9 divided by 8 multiplied by 911.5 angstroms, right? So this is the wavelength emitted in case of the second line of Lyman series, right? Okay, I'm sure it's again clear to you. This is the wavelength emitted in the second line of Lyman series, right? Okay. Let me know fast in the chat box if it is clear. Let me know fast. There are a few more things which I need to show you. Then we'll do some questions. Walaikum salam, Mac. Hello, Saraswati. How are you? Perfect, guys. Wonderful. All right, guys, wonderful. So now let's talk about one more thing. That's something which I call as series limit. That's something called as series limit. What is series limit? Series limit is basically, it is a terminology given to shortest wavelength. For example, there's a question asked. Calculate the shortest wavelength emitted in case of Lyman series. In case of Lyman series, calculate the shortest wavelength emitted. The question can be asked like this. Calculate the shortest wavelength emitted in case of Lyman series. Or it can be framed like this. Calculate the series limit in case of Lyman series. Whenever you see this term series limit, that means you are going to calculate the shortest wavelength emitted, right? And when can be the wavelength emitted shortest? You know, you have discussed one formula, delta E is equal to hc divided by lambda, right? Lambda can be only shortest if delta E is maximum, if energy gap is maximum. And in case of Lyman series, what is the maximum energy gap? In case of Lyman series, can I say the maximum energy gap is when the electron makes a transition from infinity to shell number 1, right? As simple as that, yeah. In case of Lyman series, I need to calculate the minimum, the shortest wavelength, right? And in case of Lyman series, the wavelength emitted will be shortest if the energy gap is maximum. And what is the maximum energy gap in case of Lyman series? When the electron makes a transition from infinity to 1. So remember, in case of Lyman series, if I need to calculate the shortest wavelength, that means the electron has to make a transition from infinity to shell number 1. Right? Okay. So people, if I need to calculate the shortest wavelength, I'll be simply using the Rydberg's formula. 1 divided by lambda minimum is equal to R. Z value is 1. 1 divided by N1 square minus 1 divided by N2 square, right? Okay, this term is 0, 1 by infinity is 0, right? So 1 divided by lambda minimum is equal to R, correct? Or I can say lambda minimum is equal to 1 divided by R, and 1 by R is nothing, that's 911.5 angstroms. So this is the minimum wavelength which can be emitted in case of Lyman series, right? Okay. Yeah? Right? Abdulaziz, just focus on this session right now. Can you let me know fast if it is clear? Can you let me know fast if it is clear? Right? Perfect, guys. So these were a few important terminologies which you must know before starting the questions, right? And before starting the questions, let me tell you one more thing. If I talk about the longest wavelength, right? How do I calculate longest wavelength in the Lyman series? First of all, the wavelength emitted can be longest only. First of all, we know delta is equal to hc divided by lambda. This wavelength emitted can be longest if delta is minimum. In case of Lyman series, what is the minimum energy gap? Can I say minimum energy gap is when the electron is making a transition from shell number 2 to shell number 1? That is the minimum energy gap in case of Lyman series. Okay. Minimum energy gap means lambda will be maximum, right? Lambda will be maximum. So if the question comes, calculate the longest wavelength in case of Lyman series. Okay. So you should think In order to calculate the longest wavelength, delta E should be minimum, right? Energy gap should be minimum in Lyman series. And when is the energy gap minimum in Lyman series? When the electron is making a transition from 2 to 1, right? So this is the transition which we'll be doing over here, 2 to 1, correct? Now, you can clearly use the Rydberg's formula, 1 divided by lambda max is equal to R, Z value is 1 divided by N1 square minus 1 divided by N2 square, 2 2s are 4, right? So 1 divided by lambda max, you'll be getting something as R multiplied by 3 divided by 4, or from here, you can calculate lambda max. So lambda max will be simply equal, take the reciprocal, it's going to be 4 divided by 3 multiplied by 1 by R value is 911.5 and it's going to be in angstroms. So this is the maximum wavelength which can be emitted in case of Lyman series, right? This is the maximum wavelength which can be emitted in the Lyman series. Just let me know in the chat box fast if it's clear to everyone, right? Let me know fast, yeah? Soumya, you can consult N. Avasthi. That's a wonderful good book for the physical chemistry numericals. Yeah? Perfect. Perfect, guys. Now, similarly, you can talk about the Balmer series. Okay, one thing which I would like to share with you. If I'll ask you something like this, just a second. If I'll ask you something like this. Okay, for example, I'm not talking about Lyman series. Let me talk about Balmer series. Let me talk about the Balmer series, right? First of all, if I talk about H alpha line of Balmer series, if I'm talking about H alpha line of Balmer series, what does it mean? H alpha line of Balmer series. That means which radiation I'm talking about. First of all, in Balmer series, what is the lower energy state of the electron? That's 2. Now I'm talking about H alpha line. I'm talking about the first line of Balmer series. First line means electron is making a transition from 3 to 2, right? Electron is making a transition from 3 to 2. So from here, you can calculate, you can use Rydberg's formula, you can get the value of lambda, which will be getting emitted, right? Okay. Absolutely. Similarly, if I talk about something called as series limit, of Balmer series. Series limit means lambda minimum. Lambda minimum means delta E maximum, energy gap maximum. What is the maximum energy gap in Balmer series? When the electron makes a transition from infinity to 2, right? So N2 value is infinity and N1 value is shell number 2. Right? Whatever wavelength will be emitted at this time, that's something which I'll be calling as this shortest wavelength emitted, or that's what I call as the series limit of Balmer series, right? Okay. Right? I'm talking about Balmer series. I'm not talking about the Lyman series. It's infinity to 2. Yeah? Similarly, if I need to calculate the longest wavelength emitted in Balmer series, longest wavelength means delta E should be minimum. Delta E minimum in Balmer series. That means electron has to make a transition from 3 to 2, right? So 3 to 2 transition of electron will emit the longest wavelength in Balmer series, right? Perfect. Clear to everyone, right? Yeah? Let me know in the chat box fast if it is clear so that I can move on to the next one. Let me know fast. Perfect, guys. Perfect. Let's move on then. Now, Lyman series, remember, Lyman series, it falls in ultraviolet region. Balmer series, it falls in visible region. Similarly, Paschen series, infrared. Brackett series, infrared, right? Okay, Fund series, far infrared, and Humphrey series also falls in far infrared region. Okay. Basically, if I talk about Lyman series, that means the electron is making a transition from electron is making a transition from higher energy state to shell number 1. And when the electron will be making a transition from higher energy state to shell number 1, it will be emitting energy. It will be energy in the form of radiation. That radiation will have certain wavelength, right? So that radiation, those radiations which are emitted in Lyman series, those fall in ultraviolet region. And the radiations which are emitted in Balmer series, those fall in visible region, right? Similarly, infrared, far infra. How do we represent it? How do we remember it? UVIIFF, right? That's how you remember it. UVIIFF, that's it, yeah? Okay? Right? This is how you'll be remembering it, correct? Now, This is a simple question, I'm sure. We have already solved these questions, right? But I'll try to solve one of the question over here. I'll try to solve one of the question among the three. I'm sure you can. Okay, let's start with the first one itself. Let's start with first one itself, right? After that, we have got more questions to solve in the today's session. This session is going to be a little bit longer. Calculate the wavelength of, this is H alpha line, this is not lambda, this is H alpha line, okay? Calculate the wavelength emitted in H alpha line of Balmer series. So first of all, if I talk about H alpha line of Balmer series, that means I'm talking about the first line of Balmer series. That means I'm talking about the first line of Balmer series. First line of Balmer series, that means the electron is making a transition from 3 to 2. 3 to 2, right? Electron is making a transition from 3 to 2. I need to calculate the wavelength emitted. So 1 divided by lambda right now is going to be equal to R. Z value for hydrogen is 1 divided by N1 square, that means 4, N2 square, that means 9. So what is the answer of this question? It's going to be 1 divided by lambda is equal to R. 9 minus 4 is 5, 5 divided by 36. So you get from here as lambda is equal to, you'll be taking the reciprocal on both the sides. So it's going to be 36 divided by 5. And 1 divided by R, 1 by R, already I've told you that's 911.5 angstroms. So this is how you'll be calculating the wavelength emitted in the H alpha line of Balmer series, right? Okay, right? Similarly, if you need to calculate the series limit of Lyman series, series limit, that means the shortest wavelength in Lyman series, that means delta E should be maximum. In Lyman series, when is the delta E maximum? When the electron makes a transition from infinity to 1. When the electron makes a transition from, in the second part of the question, the electron is making a transition from infinity to 1, and lower energy state I represent by N1, higher energy state I represent by infinity. Now you can use the Rydberg's formula, you can get the wavelength emitted, right? Similarly, the last one also you can do, H beta line of Postron. H beta line of Postron. What is H beta line of Postron? First of all, if I'll ask you. H beta line of Postron, I'm writing it over here, H beta line of Postron. That means second line of Postron series. First thing, in the Postron series, N1 value is 3, right? Lower energy state is 3. First line of Postron means 4 to 3. Second line of Postron means 5 to 3. So electron right now is making a transition from 5 to 3. Now you have N1 value, you have N2 value. You can use the Rydberg's formula. You can get the wavelength emitted over here, right? As simple as that. I'm sure it's clear to everyone, right? Now people, comes one more thing. What is that? Okay, this is the question. Let's try to solve this question. Okay, this is a special type of question. This is also asked frequently in your examination, right? How to approach to this sort of a question. Understand properly, how will I be approaching it? See, what transition in hydrogen spectrum? So basically, I've got something as hydrogen spectrum. Okay, what transition in hydrogen spectrum would have same wavelength as the Balmer transition? N is equal to 4 to N is equal to 2 in case of He positive spectrum. So in case of He positive spectrum, the electron is making a transition from 4 to 2. So higher energy state N2 is 4, lower energy state N1 is 2. In the He positive spectrum, the electron is making a transition from 4 to 2, right? When the electron makes a transition from 4 to 2, in case of He positive, it will be definitely emitting some radiation, which will be having some wavelength. Let's say the wavelength emitted is lambda. Now I need to see what should be the transition of an electron in hydrogen spectrum so that the electron emits the same wavelength lambda, right? What should be the possible transition in the hydrogen spectrum such that electron emits the same radiation, right? Electron emits the same radiation which will be having same wavelength lambda, right? I'm assuming in hydrogen spectrum the electron is making a transition from N2 to N1. If the electron is making a transition from N2 to N1, let's assume the wavelength of the radiation emitted is same as that of this. That's also lambda, right? Okay. Now people, what I'll be doing, I'll be using the Rydberg's formula for this as well as this separately. I'll be writing 1 divided by lambda is equal to R. Z value for hydrogen is 1. 1 divided by N1 square minus 1 divided by N2 square, right? In case of this, it's going to be 1 divided by lambda is equal to R. Z square. For helium, Z value is 2, so 2 ka square is 4 multiplied by 1 upon N1 square, N1 is 2, minus 1 upon N2 square. N1 ka square, that means 2 2s are 4, N2 square means 16, right? Okay, so people, I can say 1 divided by lambda is equal to R. If I multiply throughout by 4, it becomes 1 divided by 1 minus 1 divided by 4, right? I'm multiplying throughout by 4, right? Now we will just compare these two equations, this one and this one. If I compare these two equations, What can I get? See, this r and this r gets cancelled. So I got 1 upon n1 square minus 1 upon n2 square is equal to 1 upon 1 minus 1 upon 4, right? This 1 upon 1 minus 1 upon 4, can I write it like this? 1 upon 1 square minus 1 upon 2 square. Just compare these two equations. That means n1 value is 1, n2 value is 2. n1 value is 1, n2 value is 2. That means in case of hydrogen spectrum, the electron has to make a transition from 2 to 1. In case of hydrogen spectrum, the electron has to make a transition from 2 to 1. Then only it can emit the wavelength which this He positive spectrum is emitting right here. Okay? So whatever wavelength is emitting when the electron is making a transition from 4 to 2 in case of He positive, right? If you want the same wavelength to get emitted in case of hydrogen atom, then the electron has to make a transition from 2 to 1 in case of hydrogen. That's something which I was supposed to calculate, right? That's something which I was supposed to calculate. So in case of hydrogen, the electron has to make a transition from 2 to 1. Then only the electron will emit the radiation which will be same as that of radiation emitted in case of He positive when electron makes a transition from 4 to 2, right? Yes? I'm sure it's clear, right? Give me some thumbs ups in the chat box. Give me some thumbs ups in the chat box if it's clear. No, Subha Lakshmi, every series is equally important for your need. Yeah. Samreen, I'll be taking the session further for like 15 to 20 more minutes. I want you to stay back because this is very important. Yeah. Perfect. Now comes one more point. Calculation of number of spectral lines. Right? What does that mean? Let me make you understand like this. Calculation of maximum number of spectral lines. For example, this is n is equal to 1. I'm talking about, for example, some hydrogen-like atom whose atomic number is Z. This is, for example, n is equal to 2, right? This, for example, n is equal to 3. This is, for example, n is equal to 4, right? This is, for example, n is equal to infinity. This is n is equal to infinity, right? For example, the electron is right now in shell number 3. The electron is right now in shell number 3, okay? The electron is in shell number 3. It has to come to shell number 1. Electron has to come to shell number 1. What all possible paths this electron has by means of which it can come to shell number 1? See guys, the first thing, the electron can directly jump from 3 to 1. That is the one possible condition. The electron can first come from 3 to 2, then it can come from 2 to 1, right? So how many possibilities are with this electron to jump from 3 to 1? Either it can directly come from 3 to 1, or first it will go to 3 to 2, then from 2 to 1. So how many total radiations will be emitted when the electron makes a transition from 3 to 1? How many total radiations will be emitted? When the electron makes a transition directly from 3 to 1, one radiation will be emitted. When it makes a transition first from 3 to 2, one more. Then from 2 to 1, one more. So total how many spectral lines do we have? We have got 3 spectral lines. Maximum spectral lines when the electron makes a transition from 3 to 1 are 3, right? So I'll be getting 3 radiations of 3 different wavelengths over here when the electron is making a transition from 3 to 1, right? Now people, you're not going to check it one by one. You're not going to check it one by one. Okay? There's a simple formula to calculate it. What is the formula? I'm writing it over here. Maximum number of spectral lines. That means maximum number of radiations. Maximum number of spectral lines, maximum number of radiations emitted when the electron makes a transition from higher energy state N2 to lower energy state N1. There's a formula to calculate it. What is the formula? What is the formula? It is N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. Divided by 2. This is the general formula which you guys will be remembering from now onwards. This is how we calculate the maximum number of spectral lines which will be getting emitted when the electron makes a transition from higher energy state N2 to lower energy state N1, right? For example, I'm asking you, the electron in hydrogen atom is making a transition from 6 to 1. The electron is making a transition from 6 to 1. How many radiations will be getting emitted in total? How many radiations will be getting emitted in total? how many radiations with different wavelengths will be getting emitted in total? You'll be using the formula. First of all, it is the lower energy state N1, this is the higher energy state N2. Use the formula, get the spectral lines. N2 minus N1, so 6 minus 1 multiplied by N2 minus N1 plus 1 divided by 2. So this minus 1 plus 1 cancel. So 6 minus 1, 5, 5, 6, 30. 30 divided by 2 is 15. So there will be maximum total 15 spectral lines when the electron will be making a transition from shell number what? 6 to shell number 1 in case of hydrogen, right? Yes. Perfect. Similarly, if I ask you, the electron is making a transition from, for example, 6 to 3. How many maximum spectral lines of different wavelengths will be emitted? Simply, this is going to be the low energy state N1, this is going to be the higher energy state N2. Use the formula, N2 minus N1, 6 minus 3, that is 3, multiplied by N2 minus N1 plus 1 divided by 2. Solve it, get the maximum number of spectral lines, right? Now people, one more typical question is asked from this concept. This was how to calculate the maximum spectral lines when electron makes a transition from higher energy state to lower energy state. Now, if you need to check something like this, for example, like this, have a look. Let's say electron is making a transition from 6 to 1, right? 6 to 1. So there will be total 15 spectral lines which the electron will be emitting, right? Now I need to check out of these 15 spectral lines, how many spectral lines fall in Lyman series? How many spectral lines fall in Balmer series? How many spectral lines fall in Paschen series? Question can be asked like this as well, right? Yes? See guys, electron is for example making a transition from 6 to 1, right? We got to know a few minutes back, total 15 spectral lines will be emitted by the electron, right? Now you need to see out of these 15 spectral lines, how many spectral lines belong to Lyman series, how many belong to Balmer series, how many belong to Paschen series, how many belong to Brackett series. There is a formula for that as well. Lines of a specific series is always equal to higher energy state minus ground state of that series, See, electron is making a transition from 6 to 1. I need to check how many spectral lines out of 15 spectral lines fall in Lyman series. I need to see how many spectral lines fall in Lyman series when the electron makes a transition from 6 to 1. Use the formula. N2 is the higher energy state, over here is 6, minus ground state of that series. What is the ground state of Lyman series? Ground state of Lyman series is 1, right? That's the ground state of Lyman series. So 6 minus 1, 5. So out of total 15 lines, there will be 5 lines which belong to what? Which belong to Lyman series, right? You need to see how many spectral lines out of these 15 spectral lines belong to Balmer series. You will say N2, which is the higher energy state, minus, what is the ground state of Balmer series? 2. So 6 minus 2 is 4. So 4 spectral lines will be belonging to Balmer series, right? Yes? Right? I'm sure it's clear to everyone, right? Absolutely, guys. Let's try to solve some questions based on the same concepts. Let's try to solve some questions so that all your concepts which we have discussed in the today's session will be cleared, right? And by solving these questions, absolutely these concepts will get cleared, right? Say, hydrogen atom in the ground state is excited by a monochromatic radiation of wavelength lambda, right? So I'm exciting the electron in the hydrogen atom, which was supposed to be in ground state. Now I'm exciting it to some higher energy state by supplying monochromatic radiation whose wavelength is lambda. On coming back to the ground state, 15 different spectral lines were observed. 15 different spectral lines were observed, right? So 15 different spectral lines are observed. 15 is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2, right? Hydrogen initially was in ground state. It was initially in ground state. Then this electron, it absorbed some monochromatic light whose wavelength is lambda. Electron went to some higher energy state, right, which is N2. Now the electron is making a transition back from N2 to N is equal to 1, right? Okay. What do I need to calculate? I need to calculate the lambda which the electron absorbed in the beginning. Yes. So we will see how will I answer this question. What is the N1 value? What is the lower energy state? Lower energy state in case is N is equal to 1, right? So I'll be simply using 15 is equal, this is N2 minus N1 is 1, right? N2, this is minus 1 plus 1, cancel out, divide by 2. So you get a quadratic over here. It is 30 is equal to N2 square minus N2. So what is the quadratic equation which I got? I got the quadratic equation n2 square minus n2 minus 30 is equal to 0. Can you solve this quadratic equation for me? Right? Can you solve this quadratic equation for me? By solving this quadratic equation, you will be getting two values of n2. One value will be 6, one value will be minus 5. Right? When you solve this quadratic equation, one value will be 6, one value will be minus 5. Minus 5 is not possible, so the higher energy state is 6. That means the electron which was in shell number 1, when I supplied some energy to this electron, it went to shell number 6. Now the electron is making a transition from 6 to 1. Electron is making a transition from 6 to 1. How much energy will be emitted? Sorry, not how much energy. What is the wavelength of the radiation emitted? Again, I'll be using what? Again, I'll be using the this Rydberg's formula. I'll say 1 divided by lambda is equal to R. Z is 1. 1 divided by n1 square is 1. n2 square is 36, right? Just solve it. Get the value of lambda from here. As simple as that. Yeah? I'm sure you got the concept. Correct? Similarly, let me show it to you one more question. Let me show you one more question. Again, a very simple one. Understand. Electron in the hydrogen atom. Electron in the hydrogen atom jumps from some higher energy level up to shell number 3. So electron is in some higher energy level. Now it's coming to shell number 3. Now it's coming to shell number 3, right? Electron is coming from higher energy level to shell number 3. If 6 spectral lines are possible for the transition, so total spectral lines which are being emitted is 6. Find the initial position of electron. See, electron was initially in N2, for example, higher energy state. Now it's making a transition to shell number 3. Okay, so how many total spectral lines are being observed? 6. So let's equate this 6 as N2 minus N1 multiplied by again N2 minus N1 plus 1 divided by 2, right? This is the formula which I'll be using, right? So 6 2s are 12 is equal to N2 value is how much? N2 value is something which I need to calculate, which is the initial position of the electron, which is the initial energy shell of the electron, right? Because the electron is making a transfer from higher to lower. That means electron initially was in higher energy state. So N2 minus N1 is 3, right? So it's N2 minus N1 is 3 plus 1 divided by 2. Just solve it, get the value, right? Sorry, it's not divided by 2. 6 2s are already I have done 12, right? So it's going to be 12 is equal to N2 minus 3 multiplied by what? N2 minus 2. Just solve it, get the value of N2 from here, right? Yes? And that N2 is basically the higher energy state. I mean, that N2 is basically the initial energy state in which electron was present. Yeah? From here you can solve, right? You'll get an equation, solve this equation, get the value of N, get the value of N2 I mean. And whatever is the N2 value, that is basically the initial energy state in which hydrogen was, in which the electron was. Yeah? I'm sure you can solve this afterwards. Okay, this is one more question. People, let's try it out. Let's check it out. Let's check it out. The question is in hydrogen-like atom. Okay, in this question you can do one mistake. In this question you can do one mistake, yeah? And what is that mistake going to be? See. In hydrogen-like atom, electron makes a transition from 4th excited state up to 2nd state. 4th excited state. People, if you remember, N is equal to 1 is called as ground state. N is equal to 2 is called as 1st excited state. N is equal to 3 means 2nd excited state. N is equal to 4, 3rd excited state. N is equal to 5, 4th excited state. 4th excited state means the electron is in 4th excited state. That means electron is in shell number 5. And it is making a transition from 4th excited state to 2nd state. It is not 2nd excited state to 2nd state. That means N1 value is 2. Lower energy state is 2. So you got to know, electron is making a transition from 5 to 2. That's why I told you be careful, right? It is 4th excited state to 2nd state. It is not 4th excited state to 2nd excited state. No, it is 4th excited state to 2nd state. That means 4th excited state is 5, 2nd state is simply 2, right? Yes? Okay, so N2 I have, N1 I have. 10 different spectral lines are obtained. Now use the formula N2 minus N1. 5 minus 2 multiplied by 5 minus 2 plus 1 divided by 2. 5 minus 2 is 3, right? 5 minus 2 is 3, 3 plus 1 is 4 divided by 2. So total 6 spectral lines are observed. Total 6 different spectral lines are observed. First one is wrong. Now out of these 6 spectral lines, how many belong to Lyman series? Sorry, how many belong to Balmer series? How many belong to Paschen series? That's something which I told you, right? How many spectral lines? Out of total 6 spectral lines, how many belong to Balmer series? Formula is N2 N2 is the higher energy state, which is 5, minus ground state of Balmer. What is the ground state of Balmer? Ground state of Balmer is 2. So 5 minus 2 is 3. So this one is correct. Number of lines belonging to Paschen series. So what is the N2? N2 is 5. Ground state of Paschen, Lyman, Balmer, Paschen, 5 minus 3 is 2, right? So this one is also correct. So B, C, D are the correct options of this question. Yeah? Do you agree with this? Do you agree with this? Yeah? So B, C, and D are the correct options of this question. And people, this is something which I'm giving you as the homework. It's a very simple question. Do let me know the answer of this question in the comment section, yeah? Once the session ends. So with this, our hydrogen spectrum is done and dusted, okay? So people, before ending the session, let me give you the quick overview of something really important, right? Okay, that is about the NEET 2023 Pro subscription. If you have not enrolled yourself in the actual Vedantu platform, how to do that, what all benefits you guys will be getting apart from the YouTube sessions if you'll enroll yourself in the actual Vedantu platform. Well people, we have got 3 different subscriptions for you, okay? First one is light subscription. What all things you'll be getting a light subscription? Let me just give you the quick overview of this. See, first of all, this is the subscription which is valid for 2 years. This is the 2-year classroom program, right? And this is the course fee for this. You do not need to pay this much amount in one go. You can pay this much amount in EMI as well. Vedantu has kept an option for this. You can pay this much amount in EMI as well, right? In this light subscription, you'll be having live interactive online classes with us apart from the YouTube sessions. YouTube session is something complimentary. I'm talking about the actual Vedantu classroom, okay? You'll be getting live online interactive classes with us, right? Test series, endless, everything will be done. Notes, assignments, study material, the best study material across India. That's what we call as Tattva material. You'll be provided with if you'll enroll in this, yeah? Right? And at the same time, if you are new to Vedantu, you have no idea of how actual Vedantu classrooms look like. People, you can give it a try for a month as well, right? You can take the subscription for the month. You just have to pay some 2,700 bucks. If you think you are getting benefited from these pro subscription classes, the actual Vedantu classroom sessions, then you can enroll in the 2-year classroom program. So you can check it out for a month first, right? Do get enrolled. It's my personal opinion for you guys to get enrolled in the 1-month pro subscription if you think you are getting, which definitely you'll be getting benefited from these sessions, right? Then you can take this 2-year classroom program, which you can pay in the form of EMI. Monthly, you'll be paying the fees. Not this much. You'll be break this in 2 years, okay? So monthly, it'll be not more than some 1,500 something, right? There is something called as Classic Pro subscription. In Classic Pro subscription, what extra benefits do we get? Do you get doubt solving on mobile app? So during the live interactive online class, right? First of all, your master teacher will be helping you out in solving the doubts. If after that also you'll be facing some sort of doubt, you just have to write your doubt in the doubt solving app. You'll be at that time given the answer of that. You'll be given the explanation of that. Okay. This is the course fee, and this is again valid for 2 years, right? It's a 2-year classroom program again. And this much amount, no need to pay in one go, pay in installments. If you are new to Vedantu, give it a try for a month. This much amount you have to pay for a month, right? Okay. And people, the last one, you get the personalized mentor as well in all the 3 subjects. This is not just for chemistry, guys. This is for all the 3 subjects, physics, chemistry, as well as biology, right? All the 3 subjects are included for 2 years, 11th, 12th, and at the same time, your crash course, okay? And you can check it out for a month, this much amount you have to pay, then you can go to the actual 2-year classroom program, right? And at the same time, how to get enrolled in this one? You simply need to click on the link which is there in the description box of the video. Whatever, you'll see the description box of this video. You need to click on the link which is there in the description box. Use the coupon code as WSPRO. If you use this coupon code as WSPRO, it's my personal coupon code, Wasim Sir's Pro subscription. If you're using this, then you'll be getting enrolled, you'll be getting directed to my batch, and at the same time, you'll be getting some 20 to 30% off as well, right? So while enrolling, do not forget to use this coupon code as WSPRO. Right? This was about the Pro subscription. There is one more link in the description box of the video. That's for the Telegram. Do click on the Telegram link, get added to the Telegram group, and stay updated about the classes. And the ones who have not liked the video yet, please and please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, right? Do share the video with your friends so that all your friends get benefited out of these sessions, okay? And do not forget to like as well as subscribe to the channel. So it was nice meeting you guys. I'll see you guys tomorrow. Okay, and tomorrow we are going to have NEET 2020 mock test, right? And day after tomorrow, there'll be one more session on the atomic structure, which is going to be lecture number 8. Okay, so till then, you guys take care. Bye bye. God bless you all. Love you all. See you soon. Bye, guys.